So we've been doing a lot of shortcuts on derivatives and doing a lot of the work, but we don't have a whole lot to show for it yet of tangible answers. And so we're going to look at some physics applications of the calculus, because pretty much physics is a branch of calculus. And what a lot of physics is someone who took the time to take out all the unnecessary information from the formulas and made them nice and slick for you. When we use calculus, we're going to take all things into consideration. Some things may cancel. Some things may not. Velocity, the first thing you need to know is velocity is the change in position with respect to time. Okay, that's what velocity is. Okay. So how does my position change as time changes? Okay. So if I wanted to find the average velocity of some object somewhere, I'm just going to find the slope between the two endpoints. This is something we've already done. This is what we did when we did average rate of change, because velocity is a rate of change. Okay? And so you can see there, delta S, that's what is normally used for position, over delta T. Basically, it's just change in Y over change in X is all this is. Again, this is for average rate. This should look really familiar. Okay? It's really only lacking one thing from derivative. So one thing that is lacking. Yeah, limit as delta x goes to 0, or delta t in this case, right? The change in time goes to nothing. Okay, that's the only thing we're missing. Okay, so let's just try a few. There's a free-falling object. It's dropped from height 100 feet. Its height s at time t is given by the position function, and we're going to figure out where these come from a little bit later this year. We're actually going to derive the function. Okay, where s is measured in feet and t is measured in seconds. Determine the average rate of change of the height over the following intervals. Okay, well, so we know we want to go from a time of 1 second to a time of 2 seconds. So if I want the average rate of change, well, what am I going to do? Well, let's just find the position at 1 second. How am I going to find the position at 1 second? Well, I have to find s of 1, which is negative 16, 1 squared plus 100. That would be the position. How do I know that? Because s stands for the position function. Okay. So if I can find the position there, we'd be pretty well off. So what is s of 1? Yeah, I was going to say this isn't that difficult. You should be able to answer that one. It's 100 minus 16, and we are in calculus. Okay, 84. 84 what in this case? It'd be 84, really seeing its position, it'd be 84 feet. Well, does that help me determine average rate of change? Well, that tells me where it is at 1 second. Let's find out where it is at the second, or at second number 2. So we would take 2 squared, which is 4, times 16, which is
what? 64.
64, but it's negative, right? So it's negative 64 plus 100. What is it? Well, that doesn't really help either. Interesting. So it's a free-falling object. We know it's at time 0, it's at 100 feet. So at time 0, it's up here at 100 feet. At 1 second, it's at 84 feet. And at 2 seconds, it's at 36. Whoa, that's a little bit of a difference. Correct? That's what how the position time graph would look. Right? So in other words, it's kind of doing one of these. Do you agree that that's what this graph should look like? Kind of looks like an upside-down parabola. Yeah, it should be. It's a reflection, right, from our math knowledge. So what do I need to know? I need to know the average rate of change from that point to that point. So if I want to know average rate of change, what should I do? Just find the average. And how will we do that? Finding the slope between those 2 points. That's average rate of change. Because we know some of them are going to be a little bit above that, and some of them are going to be a little bit below that, but they will average out to whatever that slope is. Well, what are my 2 points? My points are 1, 84 and 2 comma 36. I got those from all this work we did over here. So all I really have to do is find the slope between those 2 points. It doesn't matter which one I call, like if you're doing slope x1, y1, does it matter how that works? Not really. It depends however you want to go about this. But which way you want to do it? You don't know. No. You're all a wealth of information today. So 84 minus 36 then. And then 1 minus 2. 84 minus 36. $48. Over? Wait a minute. So it's negative 48. Well, I would agree that that's the slope of that line would definitely be a negative slope if I were actually to have one in here. It's velocity, though. Huh. My change in position with respect to time is negative 48? Yeah, it's fine, because it is falling, so we assume we kind of use the ground as, actually the ground is kind of 0, and it was up at 100, so it is getting towards 0, so it is going in a negative direction. And what would the label be on something like this? Very good. How do you know it? Because feet was this top number, right? And this bottom number was represented by seconds, so it is feet per second. So that's velocity. That's the average velocity from here to here. So at some points, was it probably less than negative 48 feet per second? And at some points, maybe a little bit more, right? But on average, that's what it was. Okay. I'm sure we could keep doing these, but should we just jump to C? I mean, that's really the same process. Should we just do that? All right. We'll just jump over to here. So we know it's 1 comma 84. We know that much. So what we really need to find out is at 1.1 comma what? So if I need the y value for 1.1, well, you substitute into the function that you have. Which is right there. So to find s of 1.1, negative 16 times 1.1 squared plus 100. So here's where your calculator is going to come in handy, so go right ahead and figure that out. Well, you don't have to just hit your calculator, you actually have to open it and attempt the calculation. 80.64. Wait a minute, how come that number is bigger than when I put 2 in? Yeah, because we went there and we said that's for 1, right? Here's 2. 1.1 would be right in here, so really I'm finding the average from there to there, right? Right, so do you see how it's going to be a different average, right? And so we're going to do, it depends on which way we want to do it, we'll do 84 minus 80.64 over 1 minus 1.1. Can we agree it's going to be negative, though? I mean, just based on the graph, we should know that it's going to be a negative answer. And I think I got negative 33.6 when I did it. So negative 33.6, and it's still feet per second. How come it's not more? It hasn't traveled as far. So what has had less effect on it? Gravity has had less effect on it at that point. Okay. So do you notice what we did is I did 1 comma 2. So basically, let's kind of erase this graph here so I can kind of see if you can notice what I was really trying to accomplish with this. Okay, does this? So we did. That point is where we were worried. So I started here, and then I brought it in a little bit, and then I brought it back in some more with these points. Because we didn't actually do letter B, right? All I'm doing is I cast it out there, and what am I doing? I'm reeling it back in. So of these 3, obviously we didn't do B, so that's not right. Of these 3, what would be the best estimate right now for the instantaneous at 1 second? See, I was reeling it back into 1. What's our best estimate right now? Negative 33.6, because that's the closest one we've got, right? That's our best estimate right now. Is that exact? Probably not, right? but it's a pretty good estimate as to what it is. Okay? So that leads us to what do we have to do if I exactly want the instantaneous? I need to go back to that formula that we just used and add in what you told me before, the limit as delta t goes to 0. Okay? If we do that, we have instantaneous velocity at any particular instant. That little deal right there. But wait a minute. Wait just a second. This should look very familiar. That's the definition of derivative. So wait a minute. That means velocity is the derivative of position. If you have the position function and you take the derivative of it, it will tell you the velocity at any given time. Okay. Well, here we go. Let's determine the velocity at 1 and 2 of a free-falling object when the position function is that. Well, what do we have to do? If we need velocity and we have position, we need to take the derivative. Now, we have a choice. We can use the definition right up there, or we do have some shortcuts, right? We're going to opt for shortcuts? Okay. So our shortcut, what rule will I be using here for my shortcut? Not product. No, I wouldn't. I would just use the power rule. Could you use product? Yeah, you could, but it's kind of probably a waste of your time. So we've got negative 32t. What do you do with the 100? Yeah, it's nothing. So negative 32t is my derivative. And s prime of t is the same thing as v of t, or velocity. They are interchangeable. So now what do? I want to know the instantaneous velocity at those points. And now that it's instantaneous, that limit got added, which makes it a derivative. That's awesome. So now s prime of 1, which is also known as v of 1, all I got to do is put 1 in if I want to find the instantaneous at a time of 1. And so it's negative 32 times 1, otherwise known as negative 32 feet per second. Is that believable based on the last problem that we did? The reeling back that we did. Is it believable that that's what it would end up at? Because back here when we had this one here was what, negative 48, and then this one was negative 33.6. So if I reel it back some more, is it believable that it would be a little bit less than that as we're bringing it in? It does. It's very believable. Okay. So what do we think about this one? V of 2, which is also known as s prime of, don't know where I was going with that, but I saved it. That's a pretty cool 2, though. Equals negative 32 times 2, otherwise known as negative 64. Does that make sense that that's more negative? In other words, again, why does that make sense that it's more negative? Why does it have a greater, well, why is the velocity, how do I want to phrase it so that you don't get confused? Why is the velocity more negative than it was before? That's probably the easiest way I can put it for now, before I bring up another word. More time has elapsed, so gravity has had a chance to do more work on it. But what does gravity actually do to an object? It accelerates it. Exactly. Uh-oh. So we got position, we got velocity. All of a sudden we're talking about this word acceleration. Oh my goodness. Okay, so here's something big. The word I didn't want to use before was speed. Speed is simply the absolute value of velocity. The key you have to understand is velocity actually has direction. It depends on which way it is going. Okay? Speed does not have direction. It's just flat out how fast are you going, or how fast is the particle going. Okay? Acceleration is actually how fast is your position with respect to time changing with respect to time. That's what acceleration is. So wait a minute, it's with respect to time again, and so then it must just be the derivative of velocity. Whoa, that is crazy. So let's determine the acceleration of a free-falling object. If the position function is that, then we will discuss the answer. So here we go. So we have to find s prime of t, but s prime of, wait, what's s again? S is position, right? So s prime of t is really just velocity, and we already did that one, right? It was negative 32t, correct? So that's the first derivative of position. The second derivative of position could be known as s double prime, correct, of t. Could be known as v prime of t. or could be known as a of t, which is the acceleration function. So wait a minute, in other words, take the derivative again. And so it is negative 32. And based on the problems that we've had, this would be feet per second, otherwise known as feet per second squared. Wait a minute. Yeah, well, yeah.
Oh wait, it's okay.
Yeah. You good? Okay. What that number, for those of you that have either had physics or are in it currently, should be a very familiar number. That is the acceleration due to gravity in one of its forms. That's in feet per second squared. Does anybody know the meters per second squared? Negative 9.8. Very good. Okay. So you might want to write those two down. So later on this year, what we're actually going to do is I'm going to start you at negative 32 feet per second squared, and we're going to build our way up to the position function, okay, which is basically the opposite of derivatives, though, and that's what the second part of calculus is. Obviously, derivatives is going in one direction. Antiderivatives would be going the other way. Okay, but keep in mind that velocity has direction, and so does acceleration. Okay, so here we go. The velocity of a car starting from rest, that means that it's not moving, okay, is given by that particular function right there. Awesome. Exactly. This problem tells us to do nothing. What I would like you to do is determine the acceleration function. If we've got velocity, what do we need to do to get acceleration? Okay, we have to derive the function, but otherwise take the derivative. Of course, we could use the definition because it's so much fun. Or we could use our shortcuts. What shortcut is most helpful for this one? Yes. Close. Quotient rule. I don't. V prime of t, otherwise known as a of t. We're just going to use quotient rule. How come that little splitting up thing doesn't work like we did before? Yeah, there's not a monomial, right, on the bottom, so we can't quite split it up like we did before. But we can take bottom times the derivative of the top minus top derivative of the bottom. I was toying with the idea of messing up there just to see if you guys would actually let me go like you said you were going to the other day. I was going to mess up right there on the derivative of the bottom to see if you were paying attention. You said you were going to let me go with mistakes the other day. I was going to see if you were actually going to let me do that. Over what? Bottom square. Should we FOIL that out? No, do not FOIL that out. Not the bottom. Leave it. So technically, if all I asked you to do was to get the acceleration function, well, there you go. I have an acceleration function. But let's simplify it. Let's see, we got 80 t plus a whole lot minus 80 t all over t plus 5. Sure. Yeah, the 80 t would cancel here. And we've got 400 over t plus 5 squared. It was then suggested that I should take the square root of the top and bottom, which of course we will not do, because then we would have to take the square root of the other side of the equation. And I don't want to take the square root of a of t. So there is our acceleration function. Well, why is that helpful? Because now someone could ask me any time that actually happens to be part of this function's domain, right? And I could tell them what the acceleration is at that time. You substitute it in for t, and you do the math. Okay? What is a particular value that I should not ask about? Negative 5. Well, that doesn't really make sense to ask about that one anyways, now does it? A time of negative 5? No. Okay. Any questions? Yes? The question is about terminal velocity. Unfortunately, our graphs will not just end because our graphs do not know that terminal velocity exists. That is your job to know when that is going to happen. We're not necessarily going to learn that in here because you have to realize we're using functions that are trying to relate all this information, so we need to know when that happens. For example, if I were to ask you on some of these for you have to find where it hits the ground. For example, that last one, we knew it did this, right? That initial one. So if you just do the math, it'll say it hits the ground there, but it'll also say it hits the ground over there because it just knows it's a parabola. That's all the function knows. And it knows it would hit at two different places. So it's your job to know that this negative time value doesn't make any sense in the problem, right? Where that one would. Right? Okay, so I think that's right along the same lines as to what you were asking about. Any other questions? Well, one more thing that we should take care of then. The reason velocity and acceleration have direction, and it's very important, especially on the AP. They test this quite a bit on the AP. Okay? Every year that I've seen, they do test it. If your acceleration is positive and your velocity is negative, what is happening? Let's say you're a particle or you're in a car, whatever. What is actually happening? Okay. Are you speeding up or slowing down? If the acceleration is positive and your velocity is negative, they are opposite of each other, correct? That would be similar to, what did I say was negative, the velocity? That would be like if you're at a stop sign that happens to be on a hill and you have a stick shift. And you let the clutch out and you start rolling backwards. Then you hit the gas to go forward. For that split second, you are going to be slow. You're going to be going backwards, but once you hit the gas to accelerate forwards, which is the opposite direction of your velocity, you could either stall out or your car is going to slow down to try and go forward, correct? Think of it that way. So if they're ever opposite each other, you're actually slowing down until they start working together. When they're working together, whether they're both positive or both negative, you are speeding up. Yes. Question? So you might want to write that down somewhere. It might be important.